Welcome to a course on complex analysis. In this lecture, we are going to see the Jordan lemma and some problem based on this Jordan lemma. Let us get into it. This Jordan lemma is also based on the residue calculation. Okay, first we find the residue of a function, and with which residue we are going to do some integration as we did in the previous lectures, right? So this Jordan lemma is also useful in evaluating the improper integral. Fine. Here is the statement of the Jordan's lemma, which is given as a theorem. Here a function has to be analytic at all the points in the upper half of the plane that are exterior to the circle, which means we have a suppose we have a circle of this form. Okay. Okay, let us take the radius to be r0. Okay, outside the circle the function has to be analytic at all the points. Okay, here f of z is analytic at all the points in the half plane, so which means this region in this, okay, since I have chosen the axis in the green color, let me just draw the points in different color. In this region the function is analytic at all the points. Okay, how is the function's behavior inside the circle? We are not sure about it. And it is given that CR denotes some semicircle, which is z equals r e to the power I times of theta, and theta lie between 0 and pi, and r is bigger than r theta. So r theta is here. We will have to choose r which is bigger than that. Okay, we have here. So if we choose this as r, somewhere we have minus r, then we have a semicircle of this form. Okay, for all points, this is not big Z, there is a typographical error here, it is small z. For all points z on this semicircle, there is a positive constant f of z smaller than or equals mr, because at the points on that CR the function is analytic. If a function is analytic in CR, of course it is continuous in, this is some finite domain, right? So it is going to be a bounded one. Okay, so the boundedness, if it is bounded, then by the boundedness we have the upper bound, that is mr, and that mr go to 0 as r approaches infinity. These are the assumptions, these are the hypotheses, this is the scenario in which we are going to do our result. Okay, so these are not to be these are not to be verified. Only when these things are happening, the result that is given here is going to be true. So this is what we'll have to prove in this Jordan lemma. Then if all these conditions are satisfied, if all these hypotheses are satisfied, then for every positive constant, be it integer, rational, irrational, be it any positive constant, which means a can take any value in the set of real numbers, then limit r approaches infinity, interval over CR, f of z e to the power I a z dz is 0. So this is what we are going to prove in this lemma. Now, in order to prove this lemma, we are going to establish something called Jordan inequality, which is given in equation 1. Okay, so first of all, what we are going to do is that we'll have to establish this is happening to be true. Okay, so based on this Jordan inequality only, we are going to prove the Jordan lemma. So first of all, we'll have to prove this Jordan inequality is true, for which we just consider, if you try to plot the graph of this y equals sine theta, so this is from 0 to pi I am plotting. Okay, since if you want you can extend it as well. Next we are plotting this one, y equals 2 theta upon pi. So if you just note it, this is the theta axis and this is the y axis, and you have the peak point which is 1 here. Okay, now y equals 2 times of this one, when your theta is pi upon 2. Okay, now in this, actually, in order to plot this, I know that this 2 upon pi is a constant, and I have theta. So it is like we have the general line equation y equals mx plus c with c equals 0 and m equals 2 upon pi. Instead of x we have theta, that's it. Okay, now to plot this line, if we just find two different points that lie on the line, and if we just join it, we are going to get the line. Okay, what happens when theta is 0? When theta is 0, I get y equals 0. So it is a straight line which passes through the origin. And when in order to find it in an easy way, let me give theta equals pi upon 2, so that my y is what? 2 upon pi multiplied with pi upon 2, that becomes 1. So this is the point. Okay, when I give my theta equals pi upon 2, I get this one. So if I try to just join this, okay, let me draw it in different color. You guys can very well notice that this is going to be a straight line of this form. So this is y equals 2 theta upon pi, and the one that I have drawn on blue color is y equals sine theta. Okay, now this is the point that actually splits this region. So from 0 to pi by 2, something is happening. Okay, what is it? The blue curve lies above the green one. What is green one? That is 2 theta upon pi, which is going to be smaller than or equals sine theta when theta takes the value in the range 0 to pi by 2. After that, the reverse is going to happen. So this is what we have. Okay, sine theta is bigger than or equals 2 theta upon pi in this region. Fine, hope you get the idea. Now, if r is bigger than theta, this is what happening. This is what we are trying to say here. Okay, here we just recall. I think if I write here, recall, if x1 is smaller than or equals x2 and f of x1 is bigger than or equals f of x2, then f is decreasing, right? So this has to be true for all x1 and x2 in some interval I. Then we say that f is decreasing in that particular interval I. So with that ideology, actually let's this be true for all x1 and x2 in I. If f of x1 is bigger than or equals f of x2, then f is decreasing on I, and if f is decreasing in I, then this is going to be true. So this is the definition. So hence it has to be a two-way thing. Now we have this one. Instead of x1 and x2, we have this sine theta and 2 theta upon pi. Okay, now for r bigger than theta, what we are going to have is that r sine theta is bigger than or equals r 2 theta upon, so r 2 theta or 2 r theta upon pi. This is going to be true. Fine, we know that e power minus x is decreasing in entire r. So if it is true in entire r, then it is true in some subintervals of r as well. Now in this interval, I am going to apply this result. So what I am going to get? E power minus r sine theta is smaller than or equals e to the power minus 2r theta upon pi. So this is what I am going to get. Okay, when and now these are real valued functions. Okay, so the things that we have here are real valued. Now, by the properties of, 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 now, by the pro Riemann integration, the inequality is preserved when you integrate. Okay, so we just apply it here. We do not do anything here. Actually, this theta is in the power only. So here also we have some typographical error. So this theta is in the power only. Okay, now we just integrate this one and see what this is what we are getting. Okay, if you just observe this integral 0 to pi e to the power minus r sine theta d theta is smaller than pi upon r. Here we have something different. So actually from this we are done with the requirement of Jordan inequality. Why? If you try to observe the area covered by the sine theta, your this area is same as that of this area, since it is symmetric about pi upon 2. So your integral 0 to pi, okay, that is going to be true for this function as well, right? So when you have to do it for this one, this can be split into 0 to pi upon 2 plus pi upon 2 to pi. So this is 2 times of integral 0 to pi upon 2. Okay, so because of the symmetry about the point pi upon 2, we have this one. So this quantity, actually here I forget to mention this d theta. So this quantity is this one. When you just take this 2 to this side, you would get your Jordan inequality. So we are done with it, right? Because of the symmetry, that is what, as I said, this is true. Now we have established Jordan inequality. Now with the help of Jordan inequality, we will now proceed to prove the Jordan's lemma. So here now we assume that all the three hypotheses are satisfied. That is, the function is analytic at the points in the upper half of the plane that are exterior to the circle, absolute of z equals r naught. Okay, and the other two things are also there, with which we write integral over CR f of z, this quantity. So z is given the notation that r e per I theta. So exponential of ia r e per I theta, and when you just try to differentiate this one, this is r e per iota times of theta. So when you differentiate this one, you would get this. So we have all these things. Okay, now we are going to make use of the boundedness. So when we do it, what are we going to get? We know by hypothesis this is there. So actually by the definition, exponential of this entire quantity, let me just take it as some notation rho. So exponential of, actually not this entire one, only this part, let me take it as rho. So exponential of I rho, which is nothing but cosine rho plus I sine rho. Okay, now we'll have to split this again and see. Here also we have some exponential part, right? So we'll have to take into consideration for all these things. And or if I just simply proceed like writing exponential of this one, which means cosine a r power e iota times of theta plus, just a minute, first of all let me just open this alone. Okay, exponential of IAR cosine theta minus, when I just take this minus inside, I would get minus AR sine theta. Now exponential of a minus b, in the sense I can just write it as exponential of IAR cosine theta multiplied with exponential of minus AR sine theta. Now when I take the absolute to this particular term, because of the exponential of this I would get this value to be equal to 1, because cosine of something plus iota times of something. So when I just take the exponential, that becomes 1. So I have only this term is left. So that is what I have here. Okay, now with the help of Jordan inequality, we just integrate it. So That is, we just take absolute here, so absolute, entire absolute here. When we do so, what are we going to get? Integral 0 to pi, and this becomes mr, and this becomes exponential of minus ar sine theta, and here we would get simply r and d theta. So this is what, when we just take this absolute to inside, this is what we are going to get when these all are constant. So when we take all these constant outside, mr e to the power minus ar sine theta, and multiplied with this quantity is multiplied with r, and when we just integrate it, we would get pi along with it. So this is what we are gonna have. Okay, now, but sorry, actually this involves, this quantity involves theta, right? So by the Jordan inequality that we have, this shall be written as, now 0 to pi we should have. So what is 0 to pi? That is smaller than or equals pi upon r. When we just substitute it, and during the simplification we get this one. Now we just take a limit, r approaches infinity to this, and by our assumption mr goes to 0 as r approaches infinity, hence the requirement is established. Okay, with which now we have a problem. We have these things. Now if you just consider the function f of z out of it, your f of z is going to be simply z upon z squared plus 2x 2z plus 2. Okay, if you just try to find out the singular points that is given by the equation z squared plus 2z plus 2 equals 0, that would give you z equals minus 1 plus or minus I. So if you just try and find it out, this is what you are going to have, out of which only one lie above the real axis and the other lie below the real axis. We are interested in the singularity that lie above real axis, that is uh, sorry, minus 1 plus I. So out of this, only this singularity lie above the real axis, so we just take this. Now we'll have to find out whether this is a simple pole or not. Yes, it has only one factor, which means it must be a simple pole. If it is a simple pole, then residue at z equals z1 to the function f of z is nothing but, since we have taken, let us denote this one as z1 and this one as z1 bar. Okay, here also we have some typographical error. Okay, so this is what you just have to remove this one and take the other thing. So z upon z1 minus, actually z minus z1 bar, and this has to be evaluated at the point z equals z1. If you just do it, you would get the residue of this function. Yes, you are done, right? Even if you just multiply e to the power whatsoever the thing that we have, IAZ. Okay, so IZ1 along with it, you simply have this, no other thing. Okay, so now what we are doing is that along with this we multiply e to the power IZ, because we need only sin x. So which means we'll have to have cosine x plus I sin x. Even if you take this way as well, this is going to be the singular point, and you have all these things, right? So you will have to substitute this point into it at all the z places, then that is your residue value. Okay, now if you just try to find out the absolute of this z1, which happens to be under root 2, so you will have to choose a radius which is bigger than under root 2, and take that semicircle as CR and all other things. Okay, again by the what Cauchy residue theorem. Okay, this is again by the Cauchy residue theorem. By Cauchy residue theorem, and doing some simple calculations, we get this one as we did in the previous lectures. Okay, from which this is what you have. Okay, here after applying Cauchy residue theorem, what should we do? We are interested in identifying x sin x, integral x sin x upon x squared plus 2x plus 2, which means we'll have to equate the imaginary parts here. When we just equate the imaginary parts, this is what we have. Okay, now what is left? We'll have to just in actually we need the integral value of this quantity. In order to do it, we'll have to make sure that this goes to 0 as r approaches infinity. Okay, this is to be proved, for which we just take the estimate. Imaginary of some complex quantity is smaller than or equals the original quantity, right? And this is happening here. And what is mr here? We just have to, we know what is our f of z, right? So based on our f of z, we'll have to estimate what this is by using the ml inequality. And here you cannot directly say that when your r go to infinity you are getting this quantity to be 0. That is not at all possible, just because you have this one which is associated with it. Okay, so that is why we should do something else. That is, we'll have to incorporate this Jordan's lemma, for which we just do some calculation and try to bring this one in this form. Here when you make your r go to infinity, this term go to 0, this term go to 0. So 0 upon some positive quantity you have, so that is that go, the entire term go to 0. Okay, so we have incorporated our Jordan lemma into it. So with which, what can we say? So with which we just say that this go to 0, so it is left. So if you just evaluate what your b1 value is, now you will have to explicitly write what is b1 value. Okay, after you write your, so actually what, z1 is what, minus 1 plus iota, and e to the power iota times of minus 1 plus iota upon minus 1 plus iota minus of minus 1 minus iota. So what we have is, sorry, here it may not be visible to you guys. So minus 1 plus iota upon, in the denominator we are just going to have 2 iota, and e to the power minus 1 minus iota. Okay, so now if you will have to expand it. So let me just note it down here. It is minus 1 plus iota upon 2 iota times of e to the power minus 1 minus iota, right? We now come to the final page. So here b1 value is what, minus 1 plus iota upon 2i e to the power minus 1 minus iota. So this is e to the power minus 1 multiplied with e to the power iota, actually the final thing. So this shall be written like that. Okay, e to the power 1 minus 1 upon 2, which is constant, we just take it outside, minus 1 plus iota upon iota that we have here. Okay, multiplied with e to the power minus iota, that is cosine 1 minus sine 1, if I am not wrong, right? So this is what now. So 1 upon 2e, so e to the power minus 1, let me just write it this way. So I'll write it as minus 1 upon iota plus iota upon iota, that becomes 1. So I'll have to multiply this quantity with cosine 1 minus sine 1. So when I just see it, minus 1 upon iota, I just multiply and divide by iota, so that becomes minus iota upon minus 1, which is simply iota. Now I'll have to multiply these things. So when I multiply these things, what I have is cosine 1 minus sine 1. Wait a minute. Minus iota times of sine 1. Yeah, right. So cosine 1 minus iota times of sine 1 plus iota cosine 1 plus sine 1, if I am not wrong. Am I right? So minus 1 upon iota means minus iota upon iota multiplied with iota. So that is minus iota upon minus 1. So yes, it is iota. So iota plus 1, and we have these things. So iota, so iota times of cosine 1, and this becomes plus sine 1, and this is cosine 1 minus iota times of sine 1. So from which what we have to do is that we'll have to take only the imaginary part. Okay, so actually we'll have to multiply 2 pi I with this. So 2 pi I b1 is going to be, so 2 gets cancelled. I have pi upon e. When I multiply I inside, what am I going, actually let me just split this here itself. So cosine 1 plus sine 1, okay, plus iota times of cosine 1 minus sine 1. Okay, now when I just multiply iota inside, what am I going to get is that, so iota times of cosine 1 plus sine 1 minus cosine 1 minus sine 1. So this is what we have. Now we'll have to take the imaginary part of this quantity. Okay. So when we just take the imaginary part of this quantity, this is pi upon e cosine 1 plus sine 1. Right. So this is what we have. Now let us examine whether the given one is here. It is the principal value, Cauchy principal value. When your Cauchy principal value is exactly same as that of your integral value, only when your function is an even function. Here the function is f of x is x sin x two. Okay. If you try to evaluate f of minus x, so minus x sine minus x and minus x whole squared plus 2 times of minus x plus 2, this is going to be x sin x upon x square minus 2x plus 2, which is not same as that of f of x. So you cannot say you have found the integral value. That is not going to be true in this case. You have just found the Cauchy principal value. So in the previous problem, our principal value and integral value were turning to be the same. So with that ideology, you may not conclude this is happening true in this case as well. Here it is not true, right? You are able to identify only the Cauchy principal value. And actually in the question, yeah, so in the question also they have said us to find the Cauchy principal value only. If they don't specify to find the Cauchy principal value, what you have to do is that you just proceed by this method. You will identify only the Cauchy principal value. Okay, whether your Cauchy principal value and the integral value are same or not, that is decided only when your function is an even function. If your function is an odd function or is neither even nor not, in that cases you cannot come to the conclusion of finding the value to the improper integral. Okay, hope you people have had a better understanding of all these things. In the upcoming things, we are going to work out problems. That is, we will do problem solving sessions in this. Thank you.